Hello everyone. In the previous lesson, we explored the smallest and the largest sigma-algebras. One could observe almost nothing. The other could observe absolutely everything. Today, I want to ask a different question. Suppose a mathematical statement fails, not once, not 10 times, not even infinitely many times. Suppose it fails infinitely many times. Should we still consider it acceptable? Most people would probably say no, but modern analysis often gives a very surprising answer. Maybe, and that tiny words lead us toward measuring probability and even the way physicists think about reality. Before talking about sigma-algebras, we need to revisit something we already know. Something infinities are countable. The natural numbers, the integer, the rational numbers. Even though they are infinite, we can still list them one by one. But the real numbers are different. There are simply too many of them. No matter how clear your list is, some real number will always escape. So today we are comparing two different sides of infinity, and this difference will turn out to be extremely important. Now comes the strange part. The rational numbers are countable. The real numbers are uncountable. If we remove every rational number from the real line, what remains? The irrational numbers, and there are still uncountably many of them. Think about it. We remove infinitely many points, yet the space is still overwhelming large. It's like removing a bucket of water from the Pacific Ocean. Yes, something disappeared, but the overall picture barely changed. This is where the physically begins. Imagine measuring the temperature of the Earth. Suppose your instrument fails at 10 locations. Probably not a big deal. Suppose it fails at 1,000 locations. Still not a disaster. Suppose it fails at every rational coordinate on Earth. Now that sounds terrifying, but remember, the ratios are still countable, and the Earth contains far more points than that. Maybe those failures are still too small to affect the global picture. This is actually the kind of question measure theory asks. Now we can finally introduce today's main character. A set is called co-countable if its complement is countable. The name sounds complicated, but the idea is simple. A co-countable set is almost the entire space. Only countably many points are missing. So instead of thinking, this set is missing points, think, this set contains almost everything. That viewpoint is much more usable. Notice what is happening. For the first time, mathematics is becoming less obsessed with individual points. Instead, we start caring about the overall structure. This idea appears everywhere. In a comic, we often ignore a tiny fraction of universal transactions. In physics, we ignore microscopic fluctuations. In statistics, we ignore rare outliers. And now analysis is beginning to do actually the same thing. Now, not because the exceptions do not exist, but because they do not significantly affect the big picture. Now we combine this idea. A measurable set will be either countable or co-countable, nothing in between. This created a sigma algebra. At first glance, it looks strange. Why would anyone choose actually these sets? Because this sigma algebra is built around one idea. Countable exceptions are acceptable. Everything inside the sigma algebra respects that physically. Everything outside does not. At this point, you might wonder, why are we spending so much time on this strange sigma algebra? Because it teaches an important habit of thought. Today we are ignoring countably many points. Later we will ignore sets of measure 0. And eventually we will talk about statements that are true almost everywhere. That paradox appears throughout modern analysis. Lebesgue integration, LP space, probability theory, even quantum machines. So today's lesson is not really about a sigma algebra. It is about learning when mathematics allow us to ignore exception. And surprisingly, then that turned out to be one of the most powerful ideas in all of analysis. And this is a big picture. Analyze is not always about every point. Something it is about the overall behavior. Co-countable sets are our first step toward this physically.